wait and ask any of you have any doubts. The EMF equation of a transformer. So you are all aware that the EMF equation of a transformer is given by EMF E is equal to, so EMF, there is a constant 4.44, so you get this constant as per what we derived. Then there is a frequency, then there is a number of turns, and then there is a maximum flux in the coil. So this is the important EMF equation of the transformer. Now depending on the which side, so if I use primary, then I say N1 is equal to E1, like this. So this is this one. Also, what is the value of maximum flux? Maximum flux is nothing but maximum flux density Vm multiplied by the area of cross section. So sometimes even this can be used, and you can substitute that. So this is the EMF equation of the transformer. So based on this, we had solved some example problems, but just for revision, let's work out one example today. So I'll just give you the example. So let me write the example. Let's call it 15-1. So what is the given data? So given data is like this. So 25 kVA, one phase transformer. So number of turns in the primary is given, that is 250. Number of turns in the secondary is given, that is 50. So primary has 250 turns and the secondary has 50 turns. That means it is a step down transformer, and the ratio also you can see 5:1. The primary is connected to supply voltage V1. So V1 is the supply voltage to the primary, that is 1200 volts. 50 Hertz supply. So what we have to determine? Calculate primary and secondary currents on full load. This is the given data, and to calculate so primary current I1 at full load FL. Similarly, calculate secondary current I2 at full load. And then we also have to calculate EMF induced in the secondary, E2. And finally, we have to calculate maximum flux in the core. So these are the four things we need to calculate. So just to review your knowledge of transformers, whatever we discussed so far, can you try and suggest answers for this? So just take 2 minutes time. Try to find out the full load current of primary, full load current of secondary, EMF induced in secondary, and then maximum flux. So I'll just give you 2 minutes time. So please work out the solution and type your answer. So for your convenience, I am also showing the EMF equation on screen. So anybody able to solve? Let's look at it. Okay, so JNTU KCV I1, you are saying 20.8 amperes. Okay. Okay, so okay, so we got some answers. So let's verify the answers. Okay. So already, if you can see in your chat window, JNTU KUCEV, they have given the answer I1, I2, E2, and maximum flux. So let's look at it and confirm the answers. So what we do, it is not very difficult. So what is the rating of the transformer? So rating of the transformer divided by voltage V1 will give the primary current. So you see, I1 full load is nothing but 25 kVA divided by 1200 volts. So here you should be careful with the units. So this is nothing but 25,000 volt amperes divided by 1200 volts. So how much is that? So let me use my calculator. $20.83. So this is the full load primary current. Now how to get the full load secondary current? For that, first you should find what is E2. So what is E2? So in this case, because there are no voltage drops, so I can say E1 is equal to V1. Normally E1 is not equal to V1. There will be a difference, but for the time being, resistance and the reactor is not given. So assuming that E1 equal to V1 equal to 1200. And what is E2? So E2 will be nothing but, see, we know E2 by E1 is equal to N2 by N1. So therefore, what is E2? So E2 is nothing but E1 into N2 by N1. That is 1200 into number of turns in the secondary is 50 and number of turns in the primary is 250. So based on this, how much is this? So this thing goes 5 times, and then 5 2s is 10, 5 4s is 20, so 240. So this is 240 volts. So because E2 is 240 volts, now I can find what is I2 full load. So how to get I2 full load? There is nothing but 25,000 volt amperes divided by 240 volts. So this will give me 25,000 divided by 240. So give me 104.17. So this is the answer for the current. So far, whatever answers submitted by JNTU KV, all are correct. Now let's look at the maximum flux. So how to get maximum flux? So I can use any one formula. So I'll use E1 equal to 4.44 N1 F maximum flux. So E1 is 1200 equal to 4.44. N1 is 250 turns. frequency is 50. Therefore, what is the maximum flux? So from this, I can calculate what is the maximum flux. So that will be, let me use my calculator, 1200 divided by 4.44 multiplied by 250 turns multiplied by 50 hertz. So I'm getting 0.0216 Webers. So that I can say 21.6 milliwebers. So almost this answer is also matched. So this was brief review of the what we have learned so far in the transformer course. So now let's come back to our main topic, this one, transformer on no load. Okay, so let's work out that one. So what happens when you are having a transformer on no load? So the transformer on no load is basically, you can see, I draw the diagram. So this is the core of the transformer. Then this is the primary winding. This is the secondary winding. Now here, if I say open circuit, then automatically here the current will be 0. So I2 is equal to 0 amperes because this is open circuited, so current cannot flow. So therefore the output power is equal to 0. That means it is on no load. There is no load connected to the transformer. So under that case, what happens? So here, of course, there is a source connected here. So because there is a source connected V1, some current I1, or let's call it I0. So actually the I1 current is nothing but, in this case specially denoted as I0 because it is a no load. Now what happens to this I0? So what they measured was that there is a voltage and there is a current and there is some phase difference between them. So what is observed was that if I take V1 as a reference, so let me draw the vector diagram. So if I take V1 as the reference like this, so vertical is considered as reference, then the I0 current is coming somewhat like this. This is I0. So this angle is called phi naught. So what is phi naught? Phi naught is the power factor angle on no load. So typically this power factor angle will be somewhere around typically equal to 80 degrees to somewhere between 80 degrees to 85 degrees or something like that. So of course it can vary below 80 also. So roughly it will be like that. Now I can resolve this into two components. So if I take the horizontal component, then the horizontal component is called I mu. And if I make the vertical component, the vertical component is called IW. Now notice that this voltage and this IW working component, they are in phase. So therefore there is going to be a power loss. So that means actually what is the input power here? So input power P is nothing but V0 I0 cos of phi naught. So this is also is nothing but V0 into IW, because you notice the cos component is nothing but the IW of it. So this is the input power to the motor. so to the transformer, but the output power is 0. So what about this input, where it is going? It is going to meet the losses in the transformer. So this is nothing but no load losses. Now the no load losses are nothing but the iron losses of the transformer. So strictly speaking, some part of copper loss also involved, because there is no copper loss in the secondary because current is 0, but then some current is flowing in the primary winding and there will be resistance, there will be a copper loss, but then this current I0 will be very, very low compared to the regular current. Therefore, copper loss is negligible. Whatever is current is power is going in, that is towards the iron loss of the transformer. But what exactly is the iron loss? So iron loss is also nothing but the core loss. That means the core is made up of an iron material and the flux in the core is alternating flux. Already we discussed the working principle of the transformer. The flux inside the core is the alternating flux. So therefore the magnetic dipoles inside the core are all the time being reorganized and rearranged. That will generate heat in the core. So the core gets heated. So whatever heat energy that is released by the core is nothing but the core losses. So the core is getting heated. So that heated core is nothing but the core losses, which we can actually measure by connecting a wattmeter at the primary. So finally, whatever you are seeing here, this is a very important vector diagram of the transformer on no load. Now the question is there any EMF induced here? So what is E2? And is there any EMF induced here? What is E1? So E1 and E2 are definitely induced, are there. So E1 is nothing but exactly what is V1 here, and E2 is nothing but, depending on the number of turns, some voltage is induced. That means if I measure the voltage here, I am able to see the transformed voltage is available. Only the current is 0. So E1 and E2 are also there. For the convenience purpose, actually strictly speaking, E1 and E2 should be drawn above, in line with the V1, but the diagram will become little bit clumsy. So to avoid confusion, so E1 and E2 both are drawn below. So these are E1 and E2 as per this. Okay, so this is about this. So let's work out some example problems to understand this. So far any doubts regarding this? Please feel free to ask if you have any doubts regarding this. Okay, so let me, if you don't have any doubts, let me give you an example problem. So let's call this example 15.2. So what is the given data? (2000 by 400 volt, one phase, 50 hertz transformer). So this transformer is given. Now on no load, no load primary current. I naught is, let's say, 1 ampere when supplied by V1 equal to 2000. So we should always note that the rated voltage and supply voltage has to be matching. Of course, you can apply slightly lesser voltage or slightly higher voltage, but then under normal conditions, whatever is the rated voltage, the supply voltage should be matching to that. Also, it is noted that the P1 or P0 is 400 watts. That means 400 watts of power is being consumed. So, therefore, based on this, determine so first we need to determine components of I naught. So I naught is having two components, so that components you have to determine. Second one, vector diagram. So let us do this. So let me quickly solve it myself instead of asking you to solve it so far. Of course, you are still free to try. So what we have here is input power P naught is nothing but, so let me write the answer in a different color, is nothing but V1 I naught, or we can also call it V naught, cos of phi naught. So from this I can determine 400 equal to 2000 into I naught. I naught is 1 ampere into cos of phi naught. So first from this I can find out what is cos phi naught. So is nothing but 400 by 2000. So that is, let me calculate. $400 divided by 2000. So I'm getting 0.2 as the cos phi. So now from this I can find out the power factor angle or hysteresis angle or whatever, no load power factor angle. It's nothing but cos inverse of 0.2. So let me try to find cos inverse of 0.2 from this. So the answer I'm getting in radians, so then multiplied by 180 and divide by pi. So I'm getting 78.5 degrees. So I was telling it will be approximately close to 80 degrees. So it is 78.5 degrees. So now let's calculate the components. So before calculating components, let me also find out the sine of phi naught. What is sine of phi naught? So simple, I just divide so sine of this I am getting 0.98. So therefore now I can find out the components of the current. So what is I naught? So I naught is nothing but it's a IW plus I mu, and these two are also vectors. So how to get the IW? So IW is nothing but I naught cos of phi naught. So that is nothing but 1 into 0.2. So that is 0.2. So this is called working component. Next, there is a magnetizing component. And as you know, the symbol is I mu. So that is nothing but I naught sine of phi naught. So that is 1 into 0.98. So that is nothing but 0.98 amperes. So to understand all these things even better way, let's draw the vector diagram. So what we have first? First I have the voltage V1, which is equal to 2000 volts, and this I will consider as the reference. If this is the reference, then I naught current is 1 ampere. So this is I naught equal to 1 ampere. So this angle we already calculated, and the angle we got is phi naught. So this is 78.5 degrees. So accordingly, now if I take the components, so the horizontal component, so this will be I mu, and this I mu will be 0.98 amperes. Similarly, the vertical component of this will be IW, and this IW value is equal to 0.2 amperes. So I hope now you know how to draw all these things. So with this we have completed this problem. So any doubts you have on this, please feel free to ask. So let's call this example 15.3. So again, let me give the So what is the given data? So the given data this time is something like this. So no load current of the transformer I naught is 5 amperes. At 0.3 power factor when supplied. So power factor 0.3 lag when supplied by the voltage of 230 volts 50 hertz. Frequency is 50 hertz. The number of turns in the primary winding is 200. So N1 is equal to. So calculate maximum flux in the what given this data, what we need to find. First one to find is maximum value of flux. Second one to find is magnetizing current, I mu. And third one to find is the core loss. So again, just take a couple of minutes. You can try this problem and try to find out these values. I mu. Okay, so let us try to find out. So what we can do first is, again I find out this. First I can directly find out the core loss. So what is core loss? P naught is nothing but V1 I naught cos phi naught. So V1 is given as 230 volts, I1 is given as 5 amperes, and then power factor is given as 0.3. So by the simple calculation, I can directly get the value of the power factor. So let me do that. So So 230 multiplied by 5 amperes multiplied by 0.3. So it gives me core loss of 345 watts. So yes. So that is 345 watts. So this is nothing but the answer for the last one. Now, how to find I mu? So first let us find sin phi. Sin phi naught is nothing but, first of all, what is phi naught? Or we can also, what is phi naught? Cos inverse of 0.3. So that is nothing but so when you use a calculator, you will get the answer in radians. So you have to be careful in dividing it by factor 185. So let me write it down on screen. So 1.266 radians. So that is nothing but 1.266 divided by pi multiplied by 180. So here, so based on that, I'll get the cos angle as 72.54 degrees. So from this, I can find what is sin phi. Therefore, sin phi naught is equal to, so let me use 0.954. So once I get sin phi naught, then I can find the magnetizing component I mu. I mu is nothing but I naught into sine of phi naught. So that is nothing but 5 into 0.954. So that is nothing but 4.77 amperes. So this answer is 4.77 amperes. So 4.75 is almost correct, but most accurate answer is 4.77. All right, now to find the flux, I have to use the EMF equation. So N1, everything is given. So 230 equal to 4.44 into number of turns is 200, frequency is 50 hertz. So multiplied by maximum flux, 5 max. So from this maximum flux I can get it. So let me just quickly calculate that. $230 divided by 4.44 multiplied by 200 turns multiplied by 50 hertz. So yes, so finally I am getting from this, therefore 0.00518, or this is nothing but 5.18 milliwebers, or 5.2 also is correct. So 5.18 milliwebers is the answer. Okay, so I hope now you are clear with this topic of transformer on no load. So we can also draw vector diagram. So there is another method to solve. So another method is to make use of the triangle. So see, what is IW? So IW is nothing but I naught into cos phi naught. So that is nothing but 5 into 0.3. So that is nothing but 1.5 amperes. So therefore you look at the triangle. So this is IW, that is 1.5 amperes. This is I naught, that is 5 amperes. And here we have the right angle, and this is phi naught. So therefore I mu, how to find I mu? Simply by Pythagoras theorem, I mu is nothing but square root of phi square minus 1.5 square. So even this also we can do that. So square root of phi square minus 1.5 square. So I'm using my calculator to solve this. So again I'm getting the same answer, 4.77 amperes. So this way also you can solve, but the way this way also you can solve. So two ways in which we can solve this. So any doubts you have about this? Otherwise we can move forward with one more problem. So if you do not have any doubts, I'll continue with another topic. So far you have understood this problem. So let me change the heading. So I'll just go to the top this thing. So today I want to extend the topic. And then here I write transformer on no load, and then transformer on load. So these two topics let's cover today. So what happens if I add load to the transformer? So let us do that. So again, let me open a new page, and in that I will discuss this topic. So here on the primary side, I have primary winding. So this is the supply. So initially, when the switch is open, so what is I1? I1 is nothing but I0. So the switch is open. So the current that is nothing but the core loss of the transformer. Now, when the switch is closed, so I close the switch. So initially there is a EMF E2 here, plus minus, and there is a induced EMF E1 here, plus minus. The magnitude of E1 and E2 are determined by the number of turns. Of course, V1 is equal to E1 because I am not considering any voltage drop in the primary at this stage. So of course, under practical transformer there is going to be a voltage drop, but for the time being we consider V1 equal to E1, and there is a E2. Now the moment I close the switch, there is a E2 and there is a load, so some current will be circulating in this. So let us denote that current as I2. So this current is I2. This current will flow in the a particular secondary circuit I2 when the switch is closed. Now correspondingly, see, product of E2 and I2 is the power that is going to the load. So the complex power. The same product E1 into I2 dash will also be flowing in the primary. So to reflect this, already we had discussed that in the working principle. So there will be another current, that is I2 dash. So the addition of I0 and I2 dash together will now become the I1 current. So what is I2 dash? So here if you take N2 turns and here if I take N1 turns, so then so my I2 dash will be equal to, so the current will be inversely proportional to the turns. So it will be I2 multiplied by, let me just look at it. If there are more turns, or in other words I2, so let me just delete this first. So this will be inversely proportional to the number of turns. So this will be N2 by N1. So if the number of turns in the secondary is increasing, yeah. So therefore, I2 dash I can always calculate by I2 actual I2 multiplied by N2 by N1. So this is again important relation. So now the vector addition we have to do. So for doing the vector addition, let me briefly look at the vector diagram also. Now the one phase load will have different power factors. So the relation between E2 and I2 will be different for different types of loads. The load may be resistive, the load may be reactive, the load may be capacitive. So for that we have to draw the diagram. So let me draw vector diagrams. So this is again very important topic. So vector diagrams of transformer on load. So first vector diagram will be resistive load. Second vector diagram will be inductive load. And the third vector diagram, let me draw one more line, capacitive load. Okay, so let us understand these diagrams. This is very important to understand these diagrams, and this will come again and again. So first, I draw the supply voltage V. This is V1 supply voltage. That is nothing but equal to E1, because V1 and E1 are for inductive load also, it will be exactly same, no difference. V1 equal to E1. Similarly, for capacitive load, again I'll write V1 equal to E1. Next, I'll draw the no load current I0. Here also the same no load current will be there, I0. And here also the same no load current will be there, I0. And you already know this angle is phi naught. The power factor angle, already we discussed, this angle is phi naught. Now IW and I mu also I can show, so maybe I'll quickly show that. So this is I mu, this is I mu, but of course they are not important for understanding this. So and then IW, so this is IW, this is IW, and this is IW. So far I just repeated exactly same diagram in all three. So now the EMF induced in the secondary, so this is E2. So strictly speaking E2 should be up, but then it is making the diagram cluttered. So that's why E2 is considered as the down, because also anyway this is two separate circuits, so I can take in any direction. So I'll just take the E2 down like this. Now depending on the type of load, so because the load is resistive here, because it's a resistive load, the I2 will be like this, in phase with E2. Because it is inductive load, I2 will be lagging E2. So this is I2 and this angle is cos of phi 2. So phi 2 is the power factor angle of the secondary. This is the angle here. Similarly, here I2 will be leading the E2. So because this is again power factor angle phi 2, that is here. So I2 is leading. So I2 leading E2 because it is a capacitive load. So here I2 lagging E2, and finally here I2 in phase with E2. So this is the first thing you should understand. Now corresponding to I2, I2 dash will be there. So we have the calculation divided by N1, N2, I can get the I2 dash. But then because the V1 and E1 are above, I'll take exactly 180 degrees opposite, I'll get I2 dash. So this one. So let me use a brighter color. So this one. This one is I2 dash. The length of the I2 dash is determined by the ratio of number of turns. That we just written that formula. And the angle of I2 dash is exactly 180 degrees opposite of I2. I2 and I2 dash are exactly 180 degrees opposite. So similarly here you see, this is 180 degrees from here. I draw, this one is I2 dash. Similarly here also I2 dash 180 degrees opposite. Here I'll get I2 dash. Now what is I1? I1 is nothing but the vector addition of I2 and I0. So if I take the vector addition of these two, so simply I complete this parallelogram, then whatever is in between this one is nothing but finally I1. Similarly here also the addition of I2 and I0, so finally it will give me I1. So you already know how to add two vectors. So similarly again addition of these two vectors. Finally you will get I1. So like this. So with this we have completed the vector diagram of transformer on load, resistive load, inductive load and capacitive load. So I hope you have understood what we have drawn here. So take 2 minutes time, look at the diagrams carefully. Try to draw the diagrams in your notes. Example 15.4. Given data. A single phase transformer having a voltage ratio of 500 by 100 volts. Has a no load current I0 of 6 amperes at 0.2 power factor lag. So the no load current is 6 amperes at 0.2 power factor lag. The secondary current I2, because it is a transformer on load, there is secondary current I2, and that secondary current given is something like 120 at 0.8 power factor lag. So what we need to determine, primary current. I1. So this is the given data for the transformer, and you need to find out the primary current I1. So let me solve this problem for you, and then we will understand how it is going. So now, because the rated voltage is 100 volts, that means I'll assume that the E2 is 100 volts. Okay, so the terminal voltage V2 or E2. So let me solve the problem here. This is the given data. So V2 E2 equal to 100 volts. So let E2 be the reference. So if E2 is a reference, then I will consider E2 as a angle is 0 degrees. So therefore, what is I2? I2 is 120 amperes at 0.8 power factor lag. So in that case, see what is cos inverse of 0.8. So this is nothing but this is a standard point in electrical engineering. Cos inverse of 0.8 is 36.87 or 36.9 degrees. So therefore, what do I get? So I can write I2 is 120 amperes at an angle of minus 36.9 degrees. This is with reference to E2. So now what is I2 dash? See, the magnitude of I2 dash. So sometime back we had discussed. So this will be 120 into, so N2 by N1, that is 100 by 500. So again, how to notice is, because this is a step down transformer, look at the voltage ratio, step down transformer, the secondary current will be more than the primary current. So therefore, this is the factor that will give me that value. So how much is this? So 120 into 100 by 5. So this is nothing but, so 5 2s are 10 and then 24 amperes. So this is 24 amperes. This is just the magnitude of I2 dash. But I want to know what is actually the I2 dash value. So now if I now look at the vector diagram. So if I take E2 as the reference, then I2 is, angle is minus or 36.9 degrees is the angle for I2. So similarly, on the other side, now if I take V1 equal to E1 as a reference, then this is exactly 180 degrees opposite. I'll get I2 dash. So this I got 24 amperes, and this angle will be 36.9 degrees, lagging V1 by that angle. So that is 24 amperes. So therefore, I can write I2 dash is nothing but 24. Now the reference is E1. So it is minus 36.9 degrees amperes. So with reference to V1 or E1, anything. So this is now I2 dash. Now what is I0? So look at this question. So 6 amperes at 0.2 power factor lag. So I0 is 6 amperes at 0.2 power factor lag. So this is under no load. So what is cos inverse of 0.2? So let me calculate cos inverse of 0.2. So this is 1.37 radians. So that radians I have to convert to degrees, 1.37 radians into 180 divided by pi. So I'll get 78.5 degrees. So let me draw the I0 now. So if I draw the I0, this is 6 amperes, this is I0, and the angle is minus 78.5 degrees. So by the way, why I am giving minus? Because V1 is reference and this is lagging. So this angle is 78.5 degrees. So therefore I0 is, so now the vector representation 6 at an angle of minus 78.5 degrees. So therefore now I can calculate the I1. So how to get I1? I1 is the vector addition of these two. So this is my I1. I0 plus I2 dash. So this vector addition. So how to do vector addition? So I1 equal to 6 angle minus 78.5 degrees plus 24 angle minus 36.9 degrees. So this addition I have to do. So for doing this addition, let me use the MATLAB interface. So remember this, you can write down I1 is 6 angle minus 78.5 degrees plus 24 angle minus 36.9 degrees. So these two quantities I want to add. So let me Octave interface so that all of you can see how I am solving this part. So I created a new file called transformer on load. So in the middle of the screen, I think you can see that. So now let me try to define this. So first I am defining I naught. So that is nothing but 6 multiplied by exp. So this is nothing but exponent form of representation. So minus 78.5 I into 180 by pi. So this is definition of I naught. And then what is I2 dash? So I2 dash is nothing but 24 into exponent of minus 36.9 degrees I into 180 by pi. Then I can calculate what is I1. I1 is nothing but I naught plus I2 dash. So I can simply save this program, and now if I run this program, so on the right hand side you can see the program is executed, we got the results. So what is I naught? 3.027 plus like this, and then I2 dash and I1 we have calculated. So I1 I am getting minus 20.9 plus 3.32. So this I1 let us calculate in terms of real and imaginary components. So I1, so I just simply make a vector of absolute value of I1 and then angle of I1. So again this angle I will convert into, oh I'm sorry, I think here it should, the factor is not 180 by pi, it is pi by 180. So I'll just change that, make that correction. Now here I have to give 180 divided by pi. So let me save and then run this program. So now I got the correct answers. So first let me clear the screen. So the final answer is 28.7 at an angle of minus 44.86 degrees. So let me transfer this code to and the output which I'm getting. So let me paste the output. Okay, so this is the output that I'm getting. So therefore, finally, I1 is nothing but 28.7 at an angle of minus 44.8 or 9 degrees. So this is the final solution for our problem. The primary current I is 28.7 amperes. So this is the answer. So any doubts regarding this? Okay, if you have no doubts, then simply let me give you some homework. So practice problems on transformer on load. So even next class, we will dedicate mostly practice problems. So if you have any doubts, feel free to ask now. Otherwise, we'll meet next class on the coming Tuesday as per the timetable. So I hope today's class was useful. I'll try to quickly share the notes with you through that website. So please log in and download the notes. Maybe by today night I'll share the notes also. Thank you.